Yeah, so right, so this is our 13th lecture, actually our 14th lecture, including the midterm. That's also considered as a class. So this is our 14th class. So in the previous one, we looked at, we continued with the topic of advanced optimizations related to caches, and we discussed four of the remaining optimizations, like merging write buffers to reduce miss penalty. This optimization is going to help in you can say when you're going to merge entries into write buffer, you are going to have space in write buffer, so the write buffer is not going to it's not going to fill quickly, which means that if you want to write anything to the write buffer, so it's not going to stop you from doing that, because it has got it has got entries in it. But if you're going to merge it, then this means that for example, if you have got four entries in your write buffer and you want to write um, four different words, and if they are all four going to occupy a different entry, then for the fifth entry you have to wait, right? But if you're going to merge write buffer, and if you have got four entries such that these four entries can be merged together, then they are all going to occupy a single entry, right? And then you have space for three more entries. So the fifth one is not going to result in stopping the processor. So the processor is going to can continue because the write buffer has got free entries. So this optimization is about miss penalty. Then we looked at compiler optimizations to reduce miss penalty. This was about how can the program be changed to reduce the miss rate. Um, there are different ways to do the same thing. So for example, if you have a sorting algorithm, sorting can be done in different ways. So you can see if you have one algorithm for sorting, it might give you a higher miss rate. If you change that algorithm, it's going to give you a different miss rate. So we looked at different examples in this eight optimization. We looked at loop interchange, simple changing the loop. The inner and outer loops is going to affect the miss rate by fusing or bringing all these entries which are part of a single memory location in a single loop is also going to have a good effect on also going to have a good cache behavior. And then also we looked at tiling in this particular scheme. So tiling and blocking is a scheme where you are not going to work on all the elements of the rows or the column when you're doing any access to rows or column, but you are going to go in a blockwise way, which is going to help obviously in matrix multiplication. Then we looked at 9 and 10, which were basically prefetching techniques, and they both were different because 9th was about hardware prefetching, which is somewhat fixed. That is going to take the next block, whatever block you are going to fetch, it's always going to take the next block and put it in the instruction stream buffer. The 10th scheme was compiler control prefetching, where there should be some extra instructions in your ISA, in your instruction set architecture, which can fetch elements from the main memory and put them into the cache. Now, the whole idea of prefetching is that you are going to bring that element before it's needed. Otherwise, if it's coming when you don't need it, then it's going to result in filling the cache. And if you bring such an item which is required much earlier than it comes, then again the processor has to wait. So it has got to be something which has to be adjusted, like we said, we did an example in the last class. Then we had a multi-cycle operation miss pipeline. The whole idea is this was then an introduction to the earlier topic of instruction level parallelism. So we started with arithmetic, then we came to instruction level parallelism, and in between we continued with memory topics to give understanding of how memories are going to work. And then we are going to come back to instruction level parallelism again, because we have some concepts about memory and something which are related over here can be understood over here. So so multi-cycle operation MIPS pipeline is basically that if you are thinking about that everything can happen in one cycle, then this is not correct, because some of the execution processes are quite complicated, so you cannot all do them in a single cycle unless you have a cycle which is going to be very big. So what we do is divide those into different stages and do that also in a pipeline way. Like for example, multiplication or division operation, so or addition operation, even for floating point numbers. So you cannot expect that operation to complete in a single cycle. So we discussed about a multi-cycle operation MIPS pipeline. Much of that I gave you as an exercise to read it yourself. I hope you have done that as well. Then in the same slide, we also introduced the topic of static scheduling. And I said I will cover it from this point: static scheduling, the compiler controlled scheduling technique. So I have graded because I'm going to do this today as well. So if you have any questions, you can ask me. Right. So the whole idea is, when you're talking about instruction level parallelism, our goal is to minimize the cycles per instruction or maximize the instruction per cycle. Right. And when you're talking about cycles, pipelines, CPI, it's actually the ideal pipeline CPI, which is the best it can have. The best CPI the pipeline can have is obviously 1, because when you're talking about everything going fine, then this means that one instruction is going to take a single cycle, right? Ideal pipeline CPI plus the stall cycles, which are because of structural hazards, plus the stall cycles which are because of data hazards, because all of these hazards are going to introduce stalls, and these stalls have to be added to that instructions, and that is going to affect the overall pipeline CPI. So there is an ideal portion over here, which is this ideal portion is basically the 1, because we are completing one instruction per cycle. But then there can be different stalls. For example, okay, so there can be architectural techniques where you can reduce structural stalls completely, but data hazards and control hazards are going to be there. So for example, if 30% of your instructions are load instructions, and then the very next instruction after load is using their result, this means for 30% of those instructions, you are going to have a single cycle stall. That's a load use hazard that we discussed earlier. So this means that you have to introduce 30 for 30% instructions. For example, if you have got 1,000 instructions, then 30% of 1,000 would be 300. So 300 more cycles in your equation here, right? And control stalls are because of the branches, and branches are always going to be there. So these 3 stalls are going to add something more to this pipeline CPI, and that's going to affect the overall CPI. But the goal here is to minimize the CPI, which means that obviously you cannot change the ideal pipeline CPI, and if there are certain stalls, you can do forwarding to reduce data stalls, but even with forwarding, there would be some stalls left. So this would be your pipeline CPI. But if you want to minimize it, then you have to do something more. Now, how to reduce that? What you can do is go for different techniques to reduce it. One technique could be to have instructions executed in parallel. So we are not going to talk about that yet, but we are going to try to see how can we exploit more instruction level parallelism, right? So what we can see here is when you're talking about control stalls, these are because branches are there in the program. And when you have a branch, you have a switch in your program. So you can move in either way. So if there is a branch instruction, what happens is that it can go to 2 different directions, and you don't know which way it's going to go. So that's the switch, or that's the, you can say, break in the flow of the program. So branches are always going to be there. So what happens when you have a branch instruction, you don't know what that next instruction is. This means that you don't know what the next to next instruction would be, and so you have to stop, right? So One way to reduce these kind of control stalls is that you try to predict what should be your next instruction, right? And try to execute those instructions before time, right? Try to see that, try to guess that this would be your next instruction, and try to go on with the flow without worrying about whether it's a branch instruction, so this should be your next instruction or not. So that is what we have to discuss. And because this is not such an easy thing to do, and you have to take care of many other things, so we are going to discuss about that first. So we talk about a basic block, which is a block without any branch instruction. So we see that basic block is a very small block, typically consisting of, on average, 3 to 6 instruction. Then you are going to always have some kind of branch instruction. This is typical for most programs, because branches are not actually just only branches. Every if else statement converts to a branch. Every for while loop converts to a branch. So there are different other constructs that convert to branch in assembly language. So you're going to see there are many branches in your code. So, and then what you do is then you try to find out the dependencies between instructions. So this was a topic that we are going to discuss today. What are dependencies? And I hope most of you have done that before as well, but still we are going to just go through that once more. These dependencies are more important, because if you want to increase the parallelism in your code, the instructional parallelism in your code, you need to find instructions that can fill in these stalls, because these stalls are just empty cycles going wasted, right? So you need to reduce these stalls, right? So there would be some empty cycles because of structural, because of hardware issues, because of data issues, and because of branches. So there would be some stall cycles left, and that is going to add or increase the CPI, but our goal is to minimize the CPI. So what we want to do is we want to fill in these gaps, but we need instructions for filling in these gaps, and we need such kind of instructions which can actually be run before those instructions, before the instructions that are written in earlier in the program order. So this is our main topic today, and we are talking about dependencies here, so data dependence, and we are talking, our main topic is data dependence, but under data dependence, we have different types of dependencies. So to determine how one instructions depend on another is actually important here, to determine how much parallelism exists in the code, because if you don't know about dependencies, then it would be hard to determine how much parallelism can be exploited. So we say that two instructions are dependent if one is somehow affecting it in the other instruction. So either by data or by its name, right? And we're going to discuss about that. But if they are dependent, then the main thing that we know is that they cannot execute in parallel, right? Even though in instruction level parallelism, we are not talking about exactly issuing both of them at the same time, but still there would be some overlap in between these two instructions. So dependencies are going to control how much parallelism you can exploit in your code. Now, so there are three types of dependencies: data dependence, name dependence, and control dependence. So when you talk about data dependence, it's actually also called as the true data dependence. Now, this is important here to understand that dependencies are a property of the program. You are always going to have dependencies in your program, right? Now, whether or not that dependence is going to actually result in a hazard, that's a different thing, right? And whether or not that hazard is actually going to introduce a delay in your program, or it's going to affect the CPI, that's also a different thing. So you can have dependencies in your program, that's always going to be there. But due to a different pipeline organization, you can always avoid data hazards, right? Like, for example, forwarding is one example. Now, if you look at two basic instructions, like if in a 5-stage pipeline, if we have two instructions like add, and add is producing a result R1, and the very next instruction is subtract, say, and subtract is using this result R1. So if you're going to draw the pipeline diagram, you're going to see actually in a 5-stage pipeline, this result is going to be stored in the write back stage, right? So write back stage is the last stage, and the the R1 that you're going to read in for subtract is going to happen in the decode stage. So actually this reading should always happen after it has been written, right? So this would mean that if you want to add if you want to schedule these two instructions, then there should be a gap of at least two instructions in between these two, so that when you are going to run subtract, the decode stage is in line with the write back stage for the add, and then in this way you can ensure that this is going to happen. So you see here we have two stalls due to data hazards, but as I've mentioned here that dependencies are always going to be there. So this is an example of a dependency, but whether or not it's going to actually create a hazard being detected, it depends on the pipeline organization. Now, if we have a pipeline organization such that we have forwarding in a pipeline organization, so we are going to see if you have forwarding, what you can do is pass on the result directly from the unit that is producing the result to the unit that is needing it. So instead of aligning the write back and the decode stage, what can happen is the execution stage of this can be aligned with the decode stage of the next, and this means you don't have to insert any stall. This is only if your pipeline organization supports forwarding. So this is the case over here, that whether that dependence is going to create a hazard, that depends on the pipeline organization, and whether it's going to create a stall, that's another thing. So even with load use hazard, what's happening is in a 5-stage pipeline that we discussed, a load use hazard is still going to result in a stall even with forwarding. So what happens is that you are actually saying that there is a stall cycle. There should be a stall cycle in between that, between these two instructions. You have to leave one instruction, one cycle empty, so load, and then there should be a stall and add. But again, because of your organization, what can happen is that this stall, instead of this stall, you can have some useful instruction from some other part of the code which can fit in this particular slot, right? And if you can fit in some instruction which is independent of load and add, so this can run before these instructions, and then what you have done is you have removed any stall cycles from your program. So this is what is mentioned over here, that whether this hazard actually causes a stall, again, that also depends on the pipeline organization. So this is very critical, and the data dependencies convey three things. It can tell you about the possibility of a hazard, that the hazard can come, and it also tells you about order in which the results must be calculated. So if two instructions are dependent, so you cannot have the second one before the first one, right? An upper bound on how much parallelism can be possible, because then you would know how much, if there is more dependencies in your program, then you obviously know that you don't have much instructions that can be shifted or that can be utilized to increase to reduce the CPI. And we're going to come to that, but let's talk about dependencies here. So again, we were talking about data dependence, but data dependence is a name which is it contains three types of dependencies here. One of them is true data dependence, sometimes also called as data dependence itself, but this is the true data dependence that is the most critical one. So we say that instruction Y is data dependent on instruction X if the following holds, that is, instruction X produces a result that may be used by instruction Y. Now, obviously, X is preceding Y, so we have X before Y in program order. So if either instruction X produces a result that may be used by instruction Y, or either instruction Y produces a result which is used by Z, and Z is X produces a result which is used by Y, and Y produces a result which is used by Z. So then Z is also dependent on X. So I'm going to repeat this thing here. So if I say we have got two instructions, so let's talk about the two instructions first. So we have add. So I'm going to write just the first register here, R1. So there are two more registers, but we are not interested in what those registers are. And we have another instruction, subtract. This instruction is, let's say, X, and this instruction is, let's say, Y. So we say, and then subtract is producing some result, but what we are interested in is it's using the result R1, right? So I have just given an example highlighting only one register. So we say that Y is dependent on X. Why? Because X is producing a result which is used by Y. So we call this as data dependence, more specifically as true data dependence. So true data dependence means, because data dependence is also a name for all types of dependencies, which include data dependence, control dependence, and name dependence, but this one is specifically called as true data dependence. So I hope you all know what we are trying to find out in this true data dependence. In true data dependence, we are seeing the flow of data. So flow of data means that you are producing some result, and next one is using next any instruction. It's not necessary that this is the very next instruction. There could be some instructions in between, add and subtract, but still Y is dependent on X, right? So let's come back. So this is our first one. Instruction X produces a result that may be used by instruction Y. The second point is instruction Y is dependent on instruction Z, and instruction Z is dependent on instruction X. One thing more, that if there are three instructions, right? And Y is dependent on Z and Z is dependent on X, then we can also say that Y is dependent on X. So if we have got three instructions here, so which means that we have got X, Z, and Y. So their order would be something like this. So X produces a result which is used by Z, and Z produces a result which is used by Y. Then again we can say that indirectly Y is dependent on X. Now this is not a direct dependence, but still this is a dependence, because actually Y is dependent on Z and Z is dependent on X. That's why Y is also dependent on X, right? So this is simple, right? This is obvious as well, that since we are saying that X is producing a result which is used by Z and Z is producing a result which is used by Y, then in other words, Y is also dependent on X. So these are two points that I've discussed over here. More importantly, what we need to focus on is this first point here, which says that instruction X. So what the main point that I want to discuss over here is this one here. So mostly we'll be looking at this one here, because 2 is an indirect dependency, which is obviously going to be there. So let's look at the program here. So let's look at this code and see how many dependencies can you find out in this code. Yes, anyone? So this is our first instruction, load. So this is a loop. This is running in a loop. But let's not discuss about the second iteration of this loop. Let's just talk about these 5 instructions and see how many dependencies can you find out. I'm talking about the true data dependency here. Okay, so let's just rename them as I1 for instruction 1 and I2 for instruction 2. So whenever you find an dependency, you can just say, I'll give you one example. Okay, so we can see here that I1 or load is producing a result, and I2, which is add, is using that result. So I would say I2 is dependent on I1 because of F0, right? So this makes sense because of F0, because you are using F0 and this is producing F0. So you're also specifying why it is dependent. Okay, so this is one example that I2 is dependent on I1. Any other? Yes. I3 on which instruction? Can you unmute yourself, Mohammed Imtiaz?
Sorry, sir. Yes, sir. Because the
I3
can you hear me, sir?
I3 is dependent on which instruction, I2 or I1? Which one?
I2.
I2, because
Yes,
of
sir.
F4.
F4, yes, sir.
Yeah. Okay, good. So again, the same thing here, that is producing a result, it's using that result, right? So I hope this concept is clear. So we can see here this add instruction is not really um, dependent on any one of them, store, add, or load, because they are all producing results for different registers, and this instruction is not using any of those registers, right? So up till now there is no true data dependence between add and load, add, or store. Okay. Okay, branch, again dependent on add, because it's producing the result and it's using that result, right? Okay, so this is what I've mentioned here in the next slide. That so sorry, these arrows have been disturbed a little bit. So actually, this is for F naught and this is for F4. So we have a dependence over here for F4, and this is for F naught. Okay, and then again there is one thing over here as well. So this is for R1 here, right? So these are dependencies that we have already also highlighted. Okay, so the dependence can be overcome, that you can remove these dependence in two different ways: maintaining a dependence but avoiding a hazard. So what you can do is let these dependencies be there in the program, but try to avoid the hazard, or eliminate a dependence by transforming the code, or what you can do is remove that hazard in its first place. So the first thing is much easier to do. What the first point is stating is, let the dependence be, but try to avoid the hazard. Try to avoid that stall, basically. By hazard, we are actually focusing on removing that stall, because stall is a difficult. The stall is a problematic thing. It's going to reduce performance. So maintain the dependence. Let the dependence be there, but try to avoid the the stalls due to those hazards. The second is eliminating a dependence by transforming the code. This is something difficult, because not every code can be written in different ways. So this is the example that I also gave in the beginning of the lecture, that for example, you want to sort a list, and for sorting you want to you have different options. So one of the option gave you say 10 100 dependencies, 100 data dependencies in your program, but then you can shift your sorting algorithm to another sorting algorithm which is doing it in a different way, and maybe because of that second algorithm you require less than 100 stall cycles. So this is the second approach, where you are going to change the code, transform the code. So but this is a difficult thing to do. So mainly what we do is we try to avoid the hazard, right? And for that, what we do is schedule the code. This is our this is the simplest thing that we can do, is try to find out instructions in the code which are not dependent, and try to fill in these slots, right? Okay, so in these examples, what we did was we are looking for dependencies where we can find names of registers matching, but it would be difficult if you're talking about the same thing. For memory, it can happen that two such memory locations have the same name, but they're referring to different locations. Or it can happen that they have different names, but they are also looking at the same memory location. So this can happen here, because if you are talking about load and store instructions, so this was simple, because what we said that we have R1 and R1. So we are talking about register names, which are easier. But if you have something, you say you are producing a result in some register, that's one thing, right? So we want to produce a result in a memory location, and we store that memory location as say 100 R2. So what's happening is you're putting the result in some memory location. Now further below you have an instruction which is um, reading something from another memory location, say 10 R6. Now this is a difficult thing to to detect at compile time what whether these two instructions are dependent or not. Obviously, load would be dependent on store because store is writing to a memory location, and load is just reading the value from that memory location. So from another memory location, of basically you don't know whether it's the same memory location. So the problem is when you're talking about memory locations, it's not easy at compile time to see whether they are the both same addresses. For example, say R2 has value of uh, R2 has a value of say 50, so that memory location is going to be 150, right? So if R2 is 50, then we just add 50 to 100 and that becomes 150. So the address becomes 150. And say if R6 is 140, then this memory location also becomes 150. So at compile time, we don't know what these register values are. So we cannot say whether load is dependent on store. But at runtime, this would be more evident because you know what these register values are and you calculate the addresses. So this is the point highlighted over here that dependencies between memory locations are difficult to detect at compile time. And this can also happen when you have two memory locations which are exactly same, but you don't know whether they are actually going to be same. So this can also happen that you have a store happening to a memory location. Say I'm just going to write the memory location, say R10 R4, right? And later on you are loading some value from 10 R4. So actually it looks like they are the same thing, but at compile time you don't know whether they are actually the same thing. Hello. So the electricity has gone as I've predicted that it's going to take 1 hour to come. So we are going to take a short break of 15 minutes, right? And then I'm going to join from another location. So I'm going to come back after 15 to 20 minutes and then we are going to start from the same here, right? So I'm going to stop my first part recording here. Let's take a break of 20 minutes and I'm going to join the same in a short while, right?